really hard time being able to understand some of the questions. Like, it was a lot of, like,
ambiguity?
I didn't have enough time to, like, just go through the debugging steps and say, like, which of these is a valid one, like, under what conditions, and like, I was just trying to run through the tests in my mind and build a program in my mind and see if it worked, and I was...
Okay, my intent was that they wouldn't take too much thought, and that there'd be one answer that kind of jumps out against the others.
I'll survive.
But and I'm dropping the 2 lowest quiz grades, but let's go through this and see what we have here. So which of the following is true about memory in linked lists? The maximum number of nodes depends, among other things, on how the list is implemented. Right, so in our PA1 we were using an array and we had a maximum of 99 or 100 nodes. And the whole reason for going to PA2 was we said that it would allow an essentially unlimited amount of nodes up to the memory of the operating system. So the maximum number of nodes depends on how you decide to implement the list. It's an artifact of what's going on underneath. The false answer is the person who implemented the list routines must decide on the maximum number of nodes. Well, that was true in PA1. We decided we could have 100 nodes, or we could have made an array with 1,000 nodes, and it's fixed. But that's only because we were implementing it with an array. In PA2, we're not deciding any fixed limit up front. We could, but we're not required to. The number of nodes is limited only by the available memory. Well, that's true in PA2, but not in PA1. PA1, we were using an array, and we limited it to 100 nodes. And so there is no limit to the number of nodes is definitely false also.
I mean, if you were to use up all of the memory on the computer, then would you run out of nodes? Or?
Yes, that's the limit to the number of nodes.
Oh. Oh, wait. Isn't the number of nodes limited only by the available memory in the operating system, and not just that?
If you implemented like in PA2, but in PA1 we implemented the linked list and you were limited to 100 nodes.
PA1 was an ADT. What was the kind that we used in PA2?
The list that we're implementing, we've been talking about as an abstract data type.
So both are both ADTs? Or abstract?
They're both implementations of an abstract list.
Okay.
But they're particular implementations. So PA1 is not an abstract linked list. It's a particular version of a linked list using an array underneath. PA2 is another particular version, a particular instance of a linked list. Make sense? Mm-hmm. Okay. So sentinel nodes. A sentinel node can simplify coding of the list routines, right? That's why we do it. It takes care of those edge cases where you have an empty list or you want to insert something in front of the first node. By having a sentinel, the list is never empty and we never insert in front of the first thing in the list. We always insert after that because that is not really a data node. Is it always the last node in the list? Absolutely not. Is it necessary to prevent overflow? I don't even know what that means. And it always points to the last node. No, it always points to the first data node. All right, question 3. A linked list is like an array but allows faster inserts and deletes. That was the whole setup for linked lists, right? We want to be able to put something in between 2 elements without having to shift everything down. A linked list is nothing like an array since n nodes require n times more memory than an array of length n. Well, that's a lot of n's and it's a lot of baloney. That's saying if you have 100 times more nodes, it takes you 100 times more memory than an array of length 100. So it's claiming that it's growing as a square or something like that. It's just ridiculous. A linked list is like an array but must be kept in sorted order. No, there's no order requirement on a linked list. Is like an array, but cannot be kept in sorted order. No, there's no sort requirement on a linked list. It's just a bunch of nodes connected together. Question 4 was the one I was hoping everybody would nail. This was the question that I thought might take some deeper thought. So when thinking of PA1's linked list, which was implemented as an array, when thinking of that as an abstract data type, which of the following would be a correct line of code with respect to an abstract data type? The whole idea of an ADT, remember, for a linked list, we had 5 red routines we were using to interface with the list. And you weren't supposed to go under that firewall and start monkeying with the implementation of the list. So these last 3 answers all require you to know how that list is implemented and interact with the mechanics of that implementation using the valid flag. first one where we're using the my_null to see if some value is equal to my_null. The last one where we're checking the valid flag and checking the data field of an index element. Those are inappropriate, right? This third entry, we're calling search and we're calling insert. And we've got them inside an if statement, and that's using that interface to the linked list. So that third one is correct. And then question 5, as an abstract data type, which of the following is not supported by the interface to a linked list? So initialization, yes, that's definitely supported. Insert and search are definitely supported. That second one, take a list and return an array of struct nodes. We could write that if we were implementing our list as an array of struct nodes. But anything else, that routine doesn't make any sense whatsoever. So that's very particular to a particular implementation. It doesn't respect it as an abstract data type. All right, so let me talk about ODP 9. So ODP 9 is implementing something we're going to be talking about this week called a hash function. You don't need to know anything about hash functions, hashes, probe values, anything like that in order to do this assignment. Okay, the description tells you everything you need to know to do this program. Your whole task is to write a function called hash. And hash takes two arguments. It takes an array of characters, a string, which we call buffer, and it takes an integer, which we call probe. And it performs the following calculation. So it takes a 7 plus the sum from I equals 0 to the length of your string minus 1 of the ASCII code of your incoming string, which is called buffer. So it adds up all those ASCII codes, it adds an extra 7. It multiplies by whatever the value of probe is, squared. And it takes all of that and calculates it modulo 13.
Weird.
What?
It's weird.
It is weird. And this is like, you know, do you want to register for a class and they say first you have to jump on 1 foot 3 times while fucking like a chicken. It's not clear why you have to do that, but if you really have to do it, you can do it, right? Okay, same idea here. It may not be clear why you're writing this function, but hopefully it's clear what the function is. So you have an array of characters called buffer coming in. You can find its length with string length. So make a for loop from 0 to string length minus 1. And buffer bracket I is a character, but you can treat it like an integer. If you add it to something, it will add the ASCII code. So you can do this summation by just adding it as if it were an int. And after you've added this together, so have a running sum, initialize it to Zep7, do a for loop to add each character, then multiply by probe twice, and probe is just an integer, and then use C's modulus function percent to reduce it modulo 13, and return that as your function value. And it should give you a number from 0 to 12 inclusive. Okay, that's all you have to do for ODP 9. Tomorrow morning, 8 o'clock is the deadline. And here's some test values you can use to see if your hash function is working correctly. If you try to hash an uppercase C, you should get the number 9. Well, C has an ASCII code of 67. So a single character, this is going to be 7 plus 67 equals 74. And you're going to multiply, and since I'm saying C comma 1, my probe is just 1, so 74 times 1 squared equals 74, and 74 modulo 13 is a remainder of 9. So hash of C, comma 1 should give you a 9. Hash of lowercase c should be ASCII code 99, 7 plus 99 equals 106, times 1 squared equals 106, and 106 modulo 13 is, I'm going to cheat and take a look, 2. One more ABC. Well, 7 plus, add each of their ASCII codes, 65, 66, 67, multiply by 1, and take that modulo 13, and you should get a 2. Sorry, a 1. So you're welcome when you're writing this function to compare your results with other people's results. I still don't want you looking at code, okay? But you can write your hash function and say, hey, I typed in my name and I used a probe of 33 and this is the value I got. Can you try yours and see if you get the same thing? You can compare like that. But if you get these 6 test cases to work, you're probably very close to correct code. So write your hash function, write a main program to test it however you like, either hardwire cases, take arguments with an fgets, whatever you like. When you think it's working, build your testable image, so link in with testbed main.o. Call your output whatever you want, main, and say assess main. And there's one ungraded test you can try, and then there's a graded test you can use to submit.
The mod 13, is that just arbitrary for this particular hash table, or what?
The whole thing's arbitrary.
Okay, cool.
Came out of my twisted little brain this morning.
I was trying to look up some information. It looks like there's a whole bunch of different ways of doing hash tables with
Oh yeah.
a specific probe, or an algorithmic probe, or a probe that uses another hash table to determine the probe.
Yeah, and that's all the stuff we're going to talk about in the next few days. All right, so is that enough information for you to do ODP 9? Cool, okay. All right, and we'll come back and talk about this in a few minutes, but I want to do some wrap up on linked lists first. So any PA2 questions so far?
So in PA1 I got my search tree, just looking through the array is pretty easy, but in PA2 I cannot for the life of me get like a while loop that while the next of the list is not equal to null to keep going through and like searching. I'm having trouble like upgrading that to the PA2 version.
Okay, what did it look like in PA1? Do you have
So in
code?
PA1 I just used a for loop, and then I just like get this node equals 0, and then this node dot next equals next node, and I use those values to go through the list, like implementing them by going like the next node at the end of my for loop every time. The next node will be equal to next node dot next.
Okay,
So,
so maybe something like this equals 0, that's your sentinel node.
Yeah.
Next equals list this dot next. That's the next node.
yeah, pretty much.
Wow, next is not equal to my null. So, should we just print?
What?
Should we just do a print, like a traversal of the list? Just print out all the elements?
Like,
So, print list next data, and then we can say this equals, or just next equals list next dot next. Something like that?
yeah. I think my main problem is that, like, obviously in the array, we could just put, like, the center node is equal to the array 0, and then the next is equal to the next value, but, like, do I have to create a new structure node and, like, say that x equals the list that we're past the next value, and then keep, like, changing that every time, or how do I have
So
a
let's see,
placeholder for that?
suppose this, well, yeah, let's just say, suppose that list is a struct node, points to a sentinel. That's what we're passing most of our routine. Let's suppose that listed as a struct node star. So I want a variable named this, which is going to point to a node. So I can say struct node star this. And same thing with next. I could say struct node star next. Those are not nodes, right? They're pointers. They don't take a lot of memory. They're just addresses where we're going to have a node eventually. So here we wanted this to point to the sentinel node, so I could do something like this equals list. And now this has the address of the sentinel node. And then I wanted to set next to whatever the sentinel node's next field was. So next equals this, arrow next. The thing that this points to, pick off the next field. And that becomes next. And then this while loop is while next not equal to null. So how do we get the data field of the thing pointed to by next?
That'd just be next arrow data.
Is next arrow data, print next arrow data. And then how do we get the next field of the thing pointed to by next?
Next arrow next.
Next arrow next. And in this case, we're setting next equal to that. There you go.
All right, thank you.
It almost starts to look like magic, right, at some point, because we've got these things that are these big structures, but they're somehow manipulatable like regular variables. That works. All right, other questions? So some general comments on lists. First of all, the list we've been working with, we've always had a sentinel node. That's not mandatory. It's a convenience. It makes it easier to deal with these edge cases. But we don't need a sentinel. We could simply make the first node our data node, and an empty list we'd simply have no nodes. Our pointer would just be null. And when we want to insert, we have to check first and see if our pointer is null, and if it is, we have to create a new node, store our data there, and then change our pointer to point to that. But you can do that. When we talk about trees, which are basically like lists with more pointers, we're going to get rid of the sentinel node. But for PA1, PA2, sentinel node helps us. So we're keeping it in there. The next observation is our nodes typically look like this. So we have some data and it points like this, and our last node is null. But instead of having our last node be null, sometimes we take our last node and we point to the first node. And we get what's called a circular list. Not very startling why it's called circular. And it's a convenience. It means that if we want to visit every node in the list, we can start from anywhere and just keep following nodes, and eventually we'll get to every node in the list. We have a danger of getting stuck in an infinite loop. if we took our current code for, say, printing the contents of a list, which says go until your next pointer is null, this will loop forever because we never find a null. So we need to do something to know that we've come back to a spot we've seen. But sometimes it's convenient to have this structure because it doesn't have this edge case where the last node points to null. And there's things you might do with arrays where that's useful, with lists where that's useful. Slightly related to this is another variation. So let's put some data in our lists. So there's our regular non-circular list. Each node has a data element and has a pointer to the next node. Sometimes it's convenient to add a third piece of data and make that a back pointer to point to the previous node. And I'll just go ahead and make this back pointer null. So now we have a node with data, next, and previous. It's a little more memory. It's sometimes a fair bit more housekeeping. But this can be convenient for us. For one thing, when we were moving through our list and we were trying to insert, for example, or let's say we wanted to delete a node. When we first looked at linked lists and we said, how do we delete a node? We said, well, we can delete the 40. So here's a 10, here's a 20, here's a 40, here's the node we want to delete. To delete this node in a singly linked list, we need to change the next pointer on the previous node. And if we've moved over to here, we needed to remember what the previous node was. So we had a pair of pointers we were using as we went through the list. With a doubly linked list, we don't need that. Once we get to the 40, if we know we want to delete this, we can get to the previous node. It's just this node dot previous. So it can clean up the coding a little bit. The other advantage is sometimes, suppose you have a sorted list, and the nature of the stuff you're looking for is that it tends to be clustered together. So you're searching for something that's somewhere in the middle of your list. Let's say your list is sorted, right? So you find this thing, you start at the beginning, you move through, you eventually get to the middle of this billion element list, and here's the thing you were looking for. Suppose the next thing you're looking for is going to be within 10 locations of this thing. Singly linked list, you go back to the beginning and you travel through all those nodes until you get there. Doubly linked list, you start at this point and you say, does it come before or after? If it comes before, you just start following backwards until you either pass the point where it should be or you find it. So if your data has this spatial locality where the consecutive searches tend to be in the same area of the list more often than not, you can get a big performance improvement with a doubly linked list. It lets you traverse backwards. That's the short version. Now there's more housekeeping to do here. Yes?
Just had a quick question. Would it be okay to implement something like this in PNC, Don't you be able to match the same prototypes?
Yeah, I'm going to say stick to singly, because I want that struct node definition not to change. There's no reason for that except that at this point, if you had asked me day one, then I could have said yes, and I could have told everybody. But at this point, because it does simplify the program to do that. So yeah, stick to singly.
You could always just create another node that contains your node.
Yeah.
To the previous.
You can probably fake it somehow.
Create a double linked list to put your nodes in.
Yeah. So how do we use this? Suppose we want to insert a new node containing the data value 30. So we do some initialization. I'm not going to get bogged down in that. We're going to say, well, this is not equal to null. If this data is bigger than the number we're trying to insert, we're going to do some things. Otherwise, we're going to say this equals this next, and loop back up. But I want to just look at this section. How do we actually insert this once this is pointing to node we want to insert before? Okay, you got the setup? So we want to create a node containing 30 and insert it right before the node pointed to by this. How many colors do I have? How many colors do I have at work? 1, 2, 3 of a kind, good. All right, so this is the node that we want to insert before. So I'm going to make a new node. So new equals malloc size of struct node or whatever. And this is going to give me a new node, which looks like this. And I'm going to say new arrow data equals 30. So here's my 30. All right, we want to sandwich this into our linked list. And I don't want to bog down on details here. I'm looking for high-level lessons. So what I want you to think about as we write these 4 lines of code is how are we getting to these lines of code, not what's the actual code. Okay, because if you want to implement this, you're going to have your own variables. You're going to do this your own way. Don't worry about the code. Think about how are we deciding what the lines of code are that we're putting on the board. So this is pointing to the 40. New is pointing to this unattached node containing a 30. That's all we've got so far. And we know that this isn't a doubly linked list. And we want to insert new right before the node called this. So we need to do the following. We need this node to point to the 40. Agreed? So I want to change this to point up there, which is new arrow this, sorry, new arrow next equals this. We also want the previous node of new to point back to the 20. We want this to point to the 20. That's new arrow previous. And how do we find that 20? It's this arrow previous. It's supposed to point to the same thing that this has pointing to by its previous. So new arrow previous equals this arrow previous. And then what else needs to change?
The next for 20.
Right, the next for the 20, instead of pointing to 40, needs to point to the 30. So this needs to change to point to the 30. What does that look like? Say again? Yeah. So this arrow previous, that's the 20, and its next should be equal to new. So this is saying, look at the node this, look at the thing that it points to, which is that node, look at its previous field. This is the previous field, so this arrow previous is the address of this node. That thing arrow next says, look at the thing at that address, which is this node, look at the next field. So this arrow, previous arrow next, is this area right here. Set that equal to new, that makes this point to here.
I didn't realize you could do that, but yeah, you can.
Yeah.
So like if you want to look two ahead, in any case, you could just say this arrow next, arrow next.
Exactly.
Wow, that's cool.
Yay. Once you grok that, you're past the big hump in the learning curve, right? Once you're starting to see the light on this, it gets easier. All right, what's the last thing we need to do?
Where are we going so far?
So those are our pointers.
Change this is previous.
Change this is previous to point to new. So instead of pointing to where it was pointing, we'll use a squiggly line here and have that point to new, and in our squiggly line we'll say this arrow previous equals new.
This feels just like adding another diode into a circuit, like
Yeah.
you just pull out the one at the wire.
Mm-hmm.
Connect the rest.
Yep.
Yeah, which is kind of cool. Basically, you have a positive and negative node on these.
Yeah. And return.
You just gotta treat it like it's a circuit, huh?
Yeah, that's one way to look at it.
Huh.
Or look at your circuits like they're code.
Oh, yes, yes.
All right, so again, right, the code itself is not the punchline, right? The punchline is look at your picture, figure out how you want to change it, and write code that corresponds to each of the changes that you make. And if you do it like this, step by step, you're less likely to get into trouble. If you just try to write down code, for example, if I do this in red before I do this in blue, my blue statement won't work. Because this changes the value of this previous, and then I use the value of this previous here. And if you accidentally put them in the other order, and you're really following your arrows, you'll see that. Because when I get to the point of saying, okay, this previous, I'm going to look at this, I'm going to look at its previous, and I'm going to see, oh, that's pointing down here. That's not what I wanted to change. So it will help keep you on that street. All right, so that's an example. So questions on that? We're probably not going to do doubly linked lists, but they're fair game for tests and stuff. And this is like all great test material, right? I can give you a picture, I can ask you to change the picture to insert a node, or I can ask you to write code corresponding to certain changes in pictures, or I can give you code and ask you to draw the picture after each line of code and show me how it changes, and I want that connection to be solid there, okay? And then once you've done this and you've got it working, you throw it in an insert routine and you delete the source code, you never look at it again. And you just know that it's gonna work. Don't delete the source code. But you don't have to go back and think about this every time that you're working with a linked list, right? That's why you're putting it inside this wrapper. So now when I want to insert something, I just call my insert routine, and I know it's going to do whatever it's supposed to do. All right. So let's talk about hashes. So, this is a big gear change. We're leaving linked lists for now. And the subject area is hashes. So what's the idea of a hash? Suppose you have an array . list data. Happens to have 13 elements in it. And this is an array of strings. So you have strings up to, I don't know, 32 characters, some length, and we're going to store these strings in this array. So data equals array of strings. And we're going to receive words from the user, so we're going to have hello, and cool, and dog, and bacon, and fun. And we're going to try to store each of these words in the array so that we can come back later and say, hey, is this word in the array or not? All right, we know one way to do that, right? Take the first word, store it here. Take the second word, store it here. Take the third word, store it here, and so on. Just throw them in the array starting from the beginning. That's really easy to code. It's very inefficient to use. Suppose you want to know, is the word bacon in my array? The only way to tell, check the first entry, check the second entry, check the third entry. Keep looking through the array until you either find your word or you run out of entries. If you have a billion things in your array, what's the worst case time it's going to take you to find something in there? It's a billion operations, right? Very inefficient. A slightly more efficient, well, a greatly more efficient way to do this is to sort your elements. If you alphabetize them, and you know you have a billion elements and you're searching for the word bacon, look at the word right in the middle of your array. And if it comes after the word bacon, you don't have to consider that second half of the array. You only have to consider the first half billion entries. Now go right in the middle of that. And if that word starts with the letter A, you know that if the word bacon is in there, it's got to be in this middle quarter. And now you've only got a quarter of a billion things to search. So that's how we play high-low. We guess a number from 1 to 107 guesses instead of 100 guesses. So we can do that if your array is sorted. Sorted arrays don't work well for inserting and deleting. That's why we do linked lists. So I want to propose a different approach to storing and retrieving things from an array. So imagine that you have a genie in your machine. Okay, magical genie, purple robes, all of that. And here's what this genie does. It doesn't grant you wishes, unfortunately. Your genie does one thing. You can give it a string and it will tell you where to store that string in the array. That's all your genie does. So here's a genie. You give it a string and it gives you back an integer. And it's going to be an integer, in this case, somewhere from 0 to 12. Okay, here's what we can do with this genie. I can say, genie, where should I store the word hello? And smoke comes out and it clears and it says, store it in index 2. So, okay, I store hello right here. And then I say, where should I store the word cool? And it says, oh, store that in index 7. So I store cool there. And dog, oh, dog should go at position 9, definitely. And bacon, bacon's got to go at 0. Okay. And where should I store fun? Store fun at position 11. So I store fun there. All right. Didn't take me long to store my data, right? Assuming the genie's fast at coming up with these locations, I get a string, I ask the genie, it gives me a number, I store my data in that position. Now I want to do a search. And I want to know if the word dog is in my list, my array. All I got to do is ask the genie, hey genie, where should I store a dog? The genie will say, store at position 9. So I go check position 9, there's my dog, took me one operation. Now I want to know if there's a giraffe in my list. I say, genie, where should I store a giraffe? It says, store giraffe at location 4. I check location 4, there's no giraffe. I don't have to look any further. I know there's no giraffe in the list. This is really efficient. Because this array has 13 elements, but it could have 13 billion elements. and every one of those 13 billion elements could be occupied. And when I say, Genie, tell me where I should store a giraffe, and it says store at a location such and such, if I look there and that location is empty, I know the giraffe isn't in any of those 13 billion locations. So this is kind of magic, right? Very, very efficient for storing and retrieving information. There's got to be a catch, right?
What's in the bottle?
What's
in the bottle?
What's in the bottle? ODP 9. That's an example Genie.
When we mod 13, does that mean we give 13 possible slots for something to be stored with that value?
Correct.
Oh, cool, okay.
Yeah. If we had 23 entries in our array, then we would mod it 20.
And you want to try and come up with index numbers that would be unique, but also completely improbable to get duplicated.
Yeah.
Okay, cool.
So here's our two questions. Question 1, how does the Genie work? Question 2, which is the $64,000 question, what happens if the Genie wants to store 2 different words at the same location? In other words, I say, where should I store an aardvark? And it says, oh, definitely store the aardvark in index 7. And I've already got something in index 7. That's going to be a problem. And in reality, I've only got 13 spots, and I've got way more than 13 words in the English language. So eventually, I'm going to run into that situation where it tells me to store something in the same spot that something else is already stored. And we're going to need to have a way to deal with that situation. All right, 5-minute break. We'll come back at 1 o'clock. We'll talk about question 1 first, and then we'll work towards question 2.
You asked me to figure out how this particular list was put there?
Say what?
Or is this randomly put up on the list, or is
As
that...
far as I know, although nothing's really random, but yeah.
And if you want to reverse engineer and solve the algorithm for how to
If you can figure out how my brain works, if you do that.
Hey, I solved Nick, everyone.
Yeah. Because then you can figure out what I was going to put on the test.
Oh boy.
And what could you do with a reverse engineered teacher?
Give me advice.
Well, that's just the start of it, though, right? You could like figure out what papers they were going to write, and, like write them first, and then like sell them to them. No.
Figure out who's going to be the next billionaire
Yeah.
place.
You just create the test for them.
Yeah.
It's like the classic Star Trek trope where you go to the person who invents something and give them the invention.
Yes. Transparent aluminum.
Right.
Or go into Inception and plant the ideas in your head.
Yeah. I finally got to see that movie. Because I watched it in the theater and it made me kind of pukey. And of all places, I finally watched it on an airplane ride. That was kind of cool.